Hey class, welcome to our first lesson of this unit. It's Introduction to Functions. That should say functions, so I'm just going to add an S at the end. A few things. This is where your homework box is going to be, so just keep that in mind. You don't have any today, so lucky you this time, but the homework will usually be in that box. There's also these success criterias. At the end of this lesson, it'll just tell you what you should be able to do. So by the end of this lesson, you'll know the difference between a relation and a function. You'll know how to represent relations in multiple different methods, such as mapping diagrams, ordered pairs, equations, and graphs. You'll be able to determine a relation is a function or not by using either the vertical line test or algebraically. Just adding on to the mapping diagrams, I'm going to teach them to you. You won't really use them on an assessment, but it's there. I'm going to teach them to you just in case. And I actually did decide that instead of having you determine the domain and range of a function, that I got rid of it. We'll do that at another time. So let's get started. The first thing I like to start with is, what is a relation? A relation is a set of ordered pairs, which are values of an independent variable paired with values of a dependent variable. Right, so you have something that's either x, is usually what we use for independent variable, paired with a value of a dependent variable y. The two things impact each other. So whatever you do to the independent variable x will impact the dependent variable y. So we have y equals x plus 3, that's a line. We have x equals y squared, that's a sideways parabola kind of thing. Right, and then you have the x squared plus y squared, which is a circle. So again, these are all three different types of relations. We'll talk about what that means later on. There's different types of relations. We have something called functions, which is what we're going to be talking about, and especially what is a function. A relation can also be denoted as a ordered pair, which is what we have at the bottom here with the 13, 5, 2, 4, 0, 6, 5, right? Those are also ordered pairs, also a way to interpret a notation. So when we talk about math, we have a lot of notations in math, which is just our way of saying these are our vocabulary. These are the words that we use when we explain math. The first thing that we have is this squiggly bracket set. When we have numbers within the squiggly bracket set, basically what it says is that it's a set of something. So if you look back at our D, notice how that it has those squiggly brackets on the end, right? This is just saying that this is a set of ordered pairs together in a function. The next thing we have is this 2 less than x. That little arrow thingy tells us that 2 is less than x. How I like to remember it is the x has the mouth facing towards it, so it must be larger, so the 2 is smaller than the x. That's just how I like to remember it. If you would like to just remember the symbol, that's fine too. Just a little trick that I use. Moving forward, we're going to do x, that little arrow again, minus 5. That's just a nice way of saying that x is less than 5. It's our short form that we use. Right? Again, the small mouth is pointing towards the x. The big mouth is pointing towards the negative 5. It should be negative 5. Sorry, I wrote in 5. Then we have negative 3 is less than x. Right? So that less than, it says that x is greater than negative 3, but it's less than 14. Right? So then x, you can either say negative 3 is less than x and x is less than 14. You can say that. You can say x is greater than negative 3 but less than 14. Right? You can say that. Or you can say x falls in between negative 3 and 14. However you want to write it is completely up to you. Those are all fair interpretations of that. So we're going to move on and talk about modeling relations. When we talk about modeling relations, right, this is something you learned in grade 10. We're going to talk about this. Bob has a summer job cutting lawns for $10 an hour. The amount he earns is related to the number of hours he works per week, right? So this, we know we've kind of seen something like this in grade 9 math. The first thing we want to figure out is, what is the independent and dependent variables here? So we want to go back and look at, okay, he's cutting $10 an hour. And how much he's earning is related to how many hours he works, right? So if we want to go back and think about what is our independent variable, it's kind of the thing that we can control, the thing that we change. So yeah, it's going to be the number of hours. He controls the number of hours he works. The dependent variable is the thing that changes when we change the independent variable. So how much he gets paid is dependent on how many hours he works. So that's going to be the dependent variable. He can control how many hours he works. He can't control his rate of pay. So then we can just go in and say, okay, then the dependent variable here is going to be the money he makes at the end. So I'm going to go in, draw a table of values, right? We have here hours worked, which is going to be our, we're going to have hours worked, which is going to be our independent variable, so our x, and then the amount of money he makes, which is going to be our y. So you have 0. If he works 0 hours, he'll make $0. If he works 1 hour, how much will he make? $10. Awesome. Again, I'm just going to do that, fill it out for 2. He's going to make $20. Oops. 3, 30. I think I went up to 4, and then it just got messy after that, so I left it, and I said, okay, 4, 40. That's our table of values, right? Just our x's and our y's, and we're just pairing them up with the amount of hours that he works versus how many he didn't work, or how much money he made. So they're two related to each other. So then we're going to go in and draw our set of ordered pairs. Our set of ordered pairs is just the coordinates, right? So we're going to go and say, okay, what's x and y? 0, 0. Then we have 1 and 10. Then we have 2 and 20, right? And then we have 3 and 30. Just the x and y's from the table of values. I'm just putting them into a set of coordinated pairs. So that if I wanted to graph this, right, I have the points that I need to graph. And I make sure I put those squiggly brackets at the end and the front to indicate that it's a set of ordered pairs. The next thing we're going to go over is the equation, right? So when we're looking at the equation, we know that this is somewhat of a linear function, right? And the reason I know that is because it's going up by a set rate every single time, and the x's are going up by a set rate every single time. So I'm going to go in and write it's y equals mx plus b. Now, let's go figure out what the m is. The m is rise over run. So how much does my y go up by every time? 10. My numbers go up by 1, right? So if you look here, we're going up by 10 each time. We're adding 10. And then on the other end, we're going up by 1. So my rise is going to be 10, and my run is going to be 1. And I'm not going to write 10 over 1. We just know that's 1, so we're going to write it in as 10x. The b is going to be 0, so I don't even write it in. But the reason that is because the y coordinates are 0, 0. It goes to the point of origin. Okay? And then I'm just going to go in. I use my coordinates, and I make the graph, and I join them together so that it gives me a linear function. You can see that right away. And the last thing we're going to go over is mapping diagrams. Mapping diagrams, super easy. You just make this oval, 2 ovals, right? And then you have your x coordinates and your y coordinates, right? And you say, okay, let's just go fill in all my x's. So 0, 1, 2, 3, 4. And then with my y's, I'm going to go and fill in all my y's. 0, 1, 10, 20, 30, 40. And then, because it's a 1-to-1, I'm just going to draw which one the x is coordinated with. So 0 coordinates with the y, 1 coordinates with the 10, 2 coordinates with the 20, 3 to the 30, 4 to the 40. With a linear function, it's pretty easy because there's only one x and one y. With the quadratic, you can actually have 2 y's for the same x, so it can vary. So when we say which of these types of models are generally preferred, right? Think about the way and what you want to show people, or what you're trying to accomplish by presenting this data. More often than not, we like to show it in a graph. I want to show people that if he works more hours, he will get more money. right? Sometimes we like to show it in an equation so that you can see the m, you can see the slope. You can show it on a mapping diagram so you can show what the equations are, or what the x's and y's are kind of corresponding to. A table of values and coordinated pairs, we might do that, but more often than not, we're going to pick our equation or our graph. It's just the easiest way to present data, if that makes any sense, and represent it. So now we're just going to move on to what a function is. So a function is a type of relation, right? So a relation is like the overarching term, and a type of relation is a function. So a relation where each of the independent, so the x values, corresponds with only one value of the dependent variable. So for any x value, there's only really one possible y value. And this becomes really important because something can be a relation and not a function, but nothing can be a function and not a relation. So a function will always be a relation, but something can be a relation and not a function. So if you're looking at one of these graphs and you look at the 2, let's go find where the x value is, or the y value. You go up, it's at 5, right? So I know that without reasonable doubt, there's only one x value one y value for that 2. So it's a function because there's only one y for that x. Okay. Let's move on to this sideways parabola. If we look at the 2, now it can be 1 point something positive, or it can also be the negative version of that same number. In this situation, this is not a function. Notice how there's 2 possible y values for the 2, so it's not a function. Because I'm just going to write this in, because there's 2 possible y's for the x. So moving on to the circle, it says, we're going to go look at the 2 again, right? And notice how the 2 can go up to 2 or to the negative 2. Again, not a function. 2, x equals 2 can either be y is equal to positive 2 or the negative 2. So you can have 2 possible y values for the x. Same thing. So the first type of test that we use to determine if something is a function is actually the vertical line test. If a relation is a function, when a vertical line is drawn anywhere on the graph, it'll only intersect with one location, right? So a vertical line anywhere on the graph, it'll only hit the graph once. An algebraic test, if a relation is a function, substituting any value for x will result in only one value of y, right? So you'll only have one value of the y if you substitute any number for the x. And we can go over what that means as well. So try maybe doing practice 1 by yourself, seeing with the vertical line test. You can pause this video here and try to do it on your own. And then come back and look at your answers. Okay, so hopefully you took a minute and you paused that video, and now you're just coming back to C. So let's do the first one. Let's do A. A, if you draw a vertical line through it, it hits that once. Let's draw 2 just for, good measure. Only hits it once. I did another one for another good measure. Right, notice how any vertical line that's drawn through that graph only hits the graph once, so we know that this is a function. There's only one y for every x, so it passes the VLT. Let's try and do the same thing with the circle. So we draw it, already failed, it passes through 2. So that is not a function. It does not pass the vertical line test. The thing that can trip you out a little bit is the 4. Technically it passes the vertical line test, but you need to make sure that all vertical lines pass the vertical line test. And I just write not a function, does not pass VLT. Then let's move on to the squiggly line. And while it looks like it might not be a function, if we actually do the stuff and we draw the vertical line, it does. This is actually a sinusoidal function. We'll be learning about it in unit like trigonometry. And yeah, it passes the VLT. So let's move on to D, right? If you look at these and you look at the numbers, this might be a little bit confusing for you, but let's just go ahead and look just at the x's. Notice how the x's don't repeat. If the x's don't repeat, that's probably a good indication that this is a function, right? So yes, there's only one corresponding x for any of the y's, right? All values of y only produce one x. I'm just going to write this in. Now let's move on to the bottom. We have all these different y values, but if you look at the x's, they're all the same. So that means that for multiple y's, you have the same x value, right? So this one does not pass the VLT. This is actually a vertical line. If you were to graph it, it would look like a straight line. So the multiple y values for 1x. See, 1 can be, so y can be 3, it can be 4, 5, or 6. So now if we go back down and look at this, you'll notice that they all have the same y value. But go and look at the x's. The x's are all different. This will pass the vertical line test because it's just a horizontal line, right? So if you go and you look at this, if you draw it out, it'll just be a horizontal line, which means that, yes, if you were to graph this one, it would lead to you passing the VLT. Or you could just say, yes, it is a function because for every x value, there's only, for every value of x, there's only one corresponding y. It might be the same y, but for every x, there's only one y. So let's do this one. This one's a little bit tricky, just because if you pick like 5, this one might not be the right number. Oh, let's actually do this one instead. Let's do this one first because that one's a little bit tricky. So the first thing is, if you look at this, you know it follows y equals mx plus b form, so you already know it's a straight line. If you say to me, Miss Saying, this is a straight line, I know it will pass the VLT, like, therefore it's a function, that is a right answer. A right-er answer would be if you actually did it algebraically. So if you go in and just pick a number, so I picked 23, and just plug it in, you should get only one value for the y. So 2 times 23 is going to be 46 plus 1, so y equals 47. Notice how that x gave you only one possible y value, so this is a function. There's only one possible y value for any given x. And you could have picked any number. I picked 23. If you picked 5, if you picked 6, they all would have been the same. Moving on. So again, I said this one was a little bit tricky just because of the number. If you picked 5, it wouldn't give you necessarily the right number. So I'm going to sub in x equals 3 because that's just the number I picked. So I put in 3 for the x. Y squared equals 25. I got 9 y squared equals 25. I want to get that y squared on its own. So I'm going to move the 9 to the other side, minus 9 on both sides. So I'm left with 25 minus 9 because 9 minus 9 cancel out. Just so you can see that. Then I'm left with y squared equals 25 minus 9, which is just 16. And I'm going to square root the y because I want to get it on its own. So I'm going to square root the 16. And the thing to remember here is when you're square rooting something, it's always plus minus, because technically if you did negative 4 squared, you'd get 16. Positive 4 squared also gives you 16. So you need to make sure you're doing the plus minus. So y is either negative 4 or positive 4. Now, notice how there's two possible y values for that 1x. This is not a function. And more often than not, when you're met with something like a y squared, it is not a function. Because there's two possible y's, or two possible solutions. I'm just going to let you write that down. If at any point you need to pause, go ahead and pause and just write stuff down as we go. Often works better that way, but I do give you some time in these videos to pause. If you need to fast forward, you can. So we're going to move on to number systems. Number systems are just numerical values can often be broken down into different types of number systems, which are like integers, whole numbers, real numbers, complex numbers. Those are 4 number systems. I just went through them. And when we talk about the way numerical values work, we often classify them as one of these. This is going to become increasingly important when we talk about domain and range. But for sure, I just want to go through this now and we'll talk about it again. So natural or whole numbers are just numbers that are either positive or whole. The reason that they're whole and positive is because they're numbers like 1, 2, 3, 4, 5. Just like the basic numbers, if we go back to elementary school, there's no decimals, there's no negatives. They're just like, how many shirts do you have? I have 3 shirts. So that is what a whole number is. How many coins do you have? You can't have half a coin. You can have negative coins. So that is what a natural or whole number is. So I'm just going to go in and write an examples in. So it could be like 1, 2, 3, all the way up to, well, not infinity because you don't want to have anything up until infinity, but whatever number, like 4, 5, 6, 7, 8, like so on and so forth. So integers, on the other hand, are positive and negative whole numbers, right? So you can have negative, you can have positive here, you can have negative 3, you can have negative 4, you can have positive 4. That's what those are. I'm just going to write that in. But no decimals. And no fractions. So an example could be negative 1, negative 2, 0, 1, 2, anything like that. And we write those as like this like Z with this like nice, it looks like a fancy Z. The N just looks like a fancy N. And then next we have real numbers. These are the ones that we've most likely been working with. They're just all numbers that fall on the number line. So that includes negatives, that includes positives, that includes any rational numbers that we have. They all fall on this line from negative infinity to positive infinity. So that does include decimals. We do write it as a fancy looking R. And remember, if you remember back to grade 9, we used to write things as x is the element of all real numbers. That's what that usually means. Then last but not least, we have the one that we don't really use unless you decide to go on and do math right later on. But they are what is called a complex number, and that includes all numbers, including imaginary units. And the only thing you really need to know about imaginary units are they are numbers that don't necessarily fall on that negative infinity, positive infinity line. They are different types of units. So x, square root of negative 1 is one of those numbers. But that's all I'm going to talk about for that for now. So what I want us to do next is just go through like an example of what type of numbers are appropriate to use. I want you to actually try doing this on your own. So if you're watching this video on your own, maybe pause it and just try going through these examples by yourself, and then we can take them up together. And then at the end, I'm just going to draw an example of a function that is a function and one that's not. I actually want you to do that one on your own as well. I'll upload them and I'll tell you what they are, a couple of them. But I want you to at least have done your own. So let's go over Bob sold N t-shirts. So this is probably going to be a natural number. And the reason that is because it's a whole number, right? You can't sell 0.5 of a t-shirt. You can't sell a negative t-shirt. So that's what that's going to be. And then P can be a real number. You can have decimals in P. You can have decimals in the type of dollars that you have, right? Measurements of objects, we always put them as real numbers because they can fall anywhere on that line, from negative to infinity to positive infinity. Time measured in seconds is going to also be a real, unless I say only seconds, not including milliseconds. If I say only seconds, then you can say that it's natural because you can't have negative numbers in seconds. Displacements. So displacement is like, it's a term in physics where you talk about the net movement of someone. I would say this is a real number because you can have negative displacements, you can have positive displacements, so on and so forth. So that would be that. Just depending on how much someone moves, someone they don't move, so on and so forth. So let's draw an example of a graph that is a function and one that's not. I would say pause this video and try doing it on your own, and then come back and we'll take this up together. So pause this video here and I will draw out our Cartesian plane and we can draw them together after. Okay, so hopefully you pause your video. So the first one I did was this little parabola, because it was just the one that I remembered from last year, right? A quadratic formula. If you go and draw a line through it, that is a function. It passes the VLT. And then the one that I decided to do for not a function was a sideways parabola, right? Doesn't pass the VLT. Even though there's the same shape, just the way that they're even put on the Cartesian plane makes it a different function. Okay? So that is it for Unit 1, Lesson 1. The homework, there is none for this one, and that's it. So hopefully you have some time to go through this stuff. If you have any questions, please ask. Thank you.